Well, good morning to those of you on the West Coast, good afternoon to those of you joining us from the East Coast, and good evening to anyone joining us from Europe or stations further east. And a very warm welcome to you all. Thank you for joining this, the 41st of our regular series of short courses on pumping topics. We've been doing these for over 4 years now. Amazing how the time flies. This one will be a little longer than some. It's lasting about 45 minutes. But it still allows us a little time at the end for a Q&A session after the presentation. Here we go. Here is a listing of the previous short courses we've run during the last 2 years. If you've missed any of them, you can get a copy of the materials from our website. Go to www.ruhrpumpen.com and follow the link to RP short courses. When you go to ruhrpumpen.com, you get to this screen. And here is the link to RP short courses. If you click on that, it takes you to this screen and you'll see all of the recent courses listed. Here I just show the latest 4, but they're all up there on the website, and you can click on any of them to download copies for viewing at your leisure. Well, this seminar is going to look at vertical pumps. As I mentioned 4 weeks ago, I quickly realized that this was too big a subject to cover in one 35 to 40-minute session, so I divided it into 2. So 4 weeks ago, we covered VS1, VS2, and VS3s, and in this session, we're going to cover VS4, 5, 6, and 7. We'll be holding a Q&A session at the end, as usual, so please use the Q&A facility at the bottom of your screen at any time during the presentation to ask any questions or make any comments. I'll address those that I can live at the end of the session, and those that I can't, I'll address by mail in the coming days. We are recording this session and we'll make it available to all attendees as a YouTube link, as well as by emailing you a PDF version of the slideshow and of the Q&A summary from both of today's sessions. Well, as I said, 4 weeks ago, we looked at the first 3, VS1, VS2, VS3. So today we're looking at VS4, VS5. So VS4, which is a volute type side discharge, a sump pump. The VS5, which is very similar to a VS4, but it's a cantilever design, which means it has a rigid, large diameter shaft and no line shaft bearings in the column. Then we'll look at VS6 pumps, diffuser double case pumps, and finally volute type double case pumps, VS7. This is effectively the same again, but a more visual representation. So first, VS4 pump. There are many manufacturers of this type of pump: Ruhrpumpen, Flowserve, Sulzer, ITT Goulds, Morelli, KSB, Amarinth, Koloska, Ivara, and literally dozens of others. In the following slides, we're going to show 2 constructions of pump: the standard construction water and effluent pumps, general industrial pumps, and the semi-engineered API 610 version. Now, most of the aforementioned manufacturers do it pretty similarly. So what I'm showing you here today is not unique to Ruhrpumpen. This is in line with our principles of making these courses educational rather than product placement. So on the left is the VSP, which stands, of course, for vertical sump pump. This is the standard construction water or effluent version. And on the right, the VSP Chem, the API 610 version for the chemical and process industries. Here's a summary slide for the standard construction pump. It does solids handling up to 41 millimeters diameter on the larger sizes. There's semi-open or closed impellers. The standard construction is cast iron and steel. It has grease lubrication for the line shaft bearings here in the column, and grease lubricated thrust bearing here. It has a threaded discharge pipe, and we thread on a 150-pound flange there. This is its sister pump, the solids handling design. Very similar in construction, but it handles solids up to 6 inches in diameter. Again, cast iron or 316 construction as standard, and 11 hydraulic sizes. Next, the API construction has semi-open and Barsky impellers. Now, in case you're not sure what a Barsky impeller is, here it is. It's a low-flow, high-head impeller. The pump's available in standard materials, so cast iron and steel, but also all the API material codes. So it'll be available in stainless steels, duplex stainless steels, even super duplex stainless steels. The bearings are either grease or external clean flush, lubricated, and the thrust bearing is either, normally it's oil lubricated, but it can be grease lubricated if you prefer. The discharge pipe is welded, can be threaded, but generally it's welded because that's what API 610 requires. And it has 150-pound or 300-pound discharge flange there. Generally, it has a circular flange, which matches, for example, a 24-inch flange that you might have on the top of a storage tank. Here's the application range. We don't need to spend very long on this one. I'll flash straight on. Now, the VSP Chem, as I mentioned, frequently installed in horizontal tanks mounted on a flange on the top. Now, usually these types of applications are for hydrocarbon transfer or for waste from the same processes. The industrial pump is commonly supplied to be mounted on open tanks. And being installed on open tanks, the industrial pump has a square mounting plate to mount on the tank structure. This is the performance range, the VSP, the standard industrial pump. Its sister pump, the non-clog, and the VSP Chem goes up to 8,400 gallons a minute, which is twice the capacity of the competition. I'll put up these range charts pretty quickly. They'll be in the hard copy you get. You can look at them in more detail there. But this is for the standard industrial pump at 60 hertz. Goes up to about 4,000 gallons a minute. Same again with the 50 hertz. Goes up to about 3,500 gallons a minute. Here the non-clog pump at 6 hertz. Got some quite big pumps in that range, a limited range, fewer hydraulics, but it's some big pumps there. 9,000 gallons a minute at 60 hertz. And same again at 50 hertz, goes up to about 8,000 gallons a minute. And here's the range chart for the API version. I've only got it at 60 hertz, I'm afraid. I do need to get a 50 hertz chart done. I think I've said that before as well. So let's look at the construction of the pump, starting at the top. Here is the motor support, which incorporates the thrust bearing down here. And the motor support is designed for NEMA C or IEC D flange motors. Here we're showing the circular type of mounting plate, and on this case it has 3 lifting lugs and earthing lugs, of course. Now looking down at the bottom of the pump, the business end, it's a cast iron casing with either cast iron or stainless steel impellers for the industrial pump, and for the API version, it has the full range of API materials. We've got a basket strainer here, which you needn't have. If it's in clean pumpage, you might choose not to have the basket strainer and be able to get your pump that much closer to the bottom of the tank, shown here, to really get the lowest possible liquid levels in the tank. Bronze line shaft bearings, grease lubricated. That's in the standard pump, and in the industrial, in the chemical pump, petrocoke tape. In the industrial and API designs, the hydraulics are from the ANSI pump range, so the standard horizontal pump hydraulics, but mounted vertically. So here on the right is the normal impeller, a semi-open radial design used in the industrial and API versions. And here on the left, the non-clog impeller with much larger flow passages. If you're handling abrasive fluids, we can fit a shaft sleeve here in the bearing housing. It's a side discharge, so it comes up here. So here is the column pipe which surrounds the line shaft. But of course, this is normally effectively empty. There's no pumpage in there. The pumpage all comes out the side discharge. The impellers are keyed to the shaft and held by an impeller nut. And on the API version, this impeller nut encompasses the complete threaded end of the shaft. On the industrial pump, the discharge, we have a threaded pipe nut here, and a 150-pound flange is threaded onto it here. And on the API version, it is welded where it passes through the mounting plate, and we have a weld neck flange here, as required by API 610. Grease lubricated line shaft bearings are the norm. There's a pipe goes down to each individual bearing. The alternative is to have an external flush, a clean flush of the bearings. So here is a pipe from the surface which runs to each individual bearing with a teed off for each bearing. There's another option which is self-flushed lubrication, where we take a tapping from the discharge pipe and feed that to each individual line shaft bearing. The two designs of sole plate. Here is the square sole plate that is, mounting plate, not sole plate, mounting plate that is supplied on the standard industrial pump. And here, the round, the circular one, which matches the drilling of an ANSI flange. Sometimes we're asked to supply a sole plate, and this sole plate would be shipped in advance of the pump so that you can set it in your foundation while you're pouring it, and you can adjust it and level it using jack screws and get your anchor holes in place, so that when the pump arrives, it's a much quicker installation process. It just sits on top of the machined sole plate. We're back at the top of the pump again. We're looking at the bearing bracket and motor support. It's a casting for grease lubricated bearings, and for oil lubricated bearings, it's a fabrication. That'll be the API version. Here is the oil bath lubricated design with a double row bearing for the API build, constant level oiler with sight glass, and with labyrinth seals below and above. Alternatively, you can have the grease lubricated bearings, a single row bearing if you're running at 4-pole or 6-pole, and a double row bearing if you're running at 2-pole speed. So all API pumps have a double row bearing. It's required by API 610. Now, if the pump is going on an open tank or pit, then there's no point in sealing this area here. There's no pumpage in this column pipe, maybe some fumes, but these fumes would also be passing up either side of the pump as well, wouldn't they? So there's no point in putting a seal in this place. But if you want, you can fit a lip seal or packing rings. Now, a pump that's mounted on a fully enclosed tank will need some sealing at the shaft penetration of the head plate to prevent vapors and fumes escaping. Now, this could be packing, or it could be a mechanical seal for process fluids. Maybe a dry running gas seal, a single wet seal, or even a dual seal, a dual wet seal. As I mentioned before, it's a conventional flange-mounted motor, either to IEC or NEMA designs. No thrust capacity required. The thrust bearing is in the pump. The motor is coupled to the pump shaft with a coupling. So on the industrial pump, it's a standard L-jaw design with an elastomeric insert here between the two flanges. And on the API version, it will be a Metastream style coupling, a metallic type coupling, either a non-spacer or a spacer coupling. So I say spacer or non-spacer. Why do I say that? Well, API 610 would require a spacer coupling here to allow you to remove the thrust bearing and any mechanical seal without having to remove the motor. But frequently these sump pumps, they've got quite small motors, and it's often easier to remove the motor than it is to get the thrust bearing and the mechanical seal out through the spacer. So it's worth considering whether or not you need a spacer really. Now, on an API pump with a mechanical seal, depending on the type of seal you've got, you might want a seal support system. Plan 74 for a gas seal, or Plan 52 or 53 for a dual seal. We frequently supply accessories such as level indicators, RTDs, and accelerometers for reading the vibration of the pump. We also manufacture jacketed pumps for where some fluids, such as molten sulfur, we need to maintain a certain temperature so they don't solidify inside the pump. And we do this with a steam jacket. The steam flows through the whole pump, heating the fluid to avoid crystallization or any change in the operating conditions. Molten sulfur pumps are product lubricated. So a tapping is taken from the discharge line and is routed to each line shaft bearing. And the steam comes in here at the top, passes first to the column jackets, passing from one section to the second, to the third, to the fourth. Then it crosses over and comes back up the jacket on the discharge pipe, exiting at the top. As you see here, it comes in, and here it exits. On sulfur pumps, mechanical seals are installed where the line shaft passes through the mounting plate to prevent sulfur fumes escaping to atmosphere, most likely a dry running gas seal. A quick look at some of the others. This is the ITT Gould's API offering. It's similar in most ways to the Ruhrpumpen, but not the same range. They only go up to 3,000 gallons a minute. The Ruhrpumpen goes up to about 8,400 gallons a minute. This is the Flowserve non-API pump. It's modifiable with some API features, and it goes up to about 6,000 gallons a minute. Flowserve also has an API model, Many of the same features as the Ruhrpumpen pump. Inducers are available if required, and it goes up to about 4,400 gallons a minute. And this is the Sulzer non-API model. I'm not actually sure if they have a full API model. It's not obvious on their website, but I think a big company like Sulzer almost definitely do. So that concludes the VS4. We'll now look at the VS5 pump, the cantilever pump. Not too much to say here. You don't come across them very often. They have a heavy-duty, self-supporting shaft, so no line shaft bearings. They're typically used in high solids content service and slurries and sulfuric acid service. Here's the FlowServe pump on the left and the Sulzer pump here on the right. There hasn't been much of a demand. There hasn't been sufficient demand for these sort of pumps for Ruhrpumpen to develop one as yet. But never say never. So that was quick on the VS5. Now the VS6, which API 610 defines as a double casing diffuser type vertically suspended pump, also commonly known as a canned suction pump or a vertical barrel pump. It's traditionally used when you have very low, even zero NPSH available at grade. It works on the basis that if you have zero NPSH at grade, then 3 meters down, you have 3 meters of NPSH available. So we make the pump long enough by putting in spool pieces here to position the first impeller low enough to give you the NPSH margin you need. But it's not just an NPSH saver. It's a space saver too. It takes about 20% of the floor area of the equivalent BB2. And it's a cost saver too. One seal, one sealing system, and it's less expensive than the equivalent BB2. But civil engineers don't like digging holes, which always seems strange to me. That's what they went to university to study, how to dig a hole, but you never know them. But of course, there can be good reasons, such as high water tables and quality of the groundwater. But if you can persuade them to dig a hole, you're winning all the way. The big users for these pumps: light hydrocarbons, C2s, C3s, C4s, condensate water in power stations, ammonia pumps, liquid oxygen, liquid nitrogen. And they're available in API 610 build and non-API, so Hydraulic Institute construction. You may well come across two different styles of VS6 pump: a radial design on the left, which is primarily European design, and the Francis vane on the right, which is predominantly an American origin pump. The American design was a spin-off from borehole pumps, which are widely used across the Americas. With borehole installations, you're trying to get as much water as possible out of as small a diameter well as possible while maximizing efficiency. Length or number of stages is just not an issue. Hence the Francis vane. High capacity, small diameter, high efficiency, but lower head per stage. Now, European manufacturers, on the other hand, they were not big into borehole pumps. We have plenty of surface water in Western and Northern Europe, so VS6 pumps were developed from horizontal process pumps, radial designs. So they tend to be shorter, with fewer stages, bigger diameter, because they're radial rather than mixed flow, so bigger diameter than their American counterparts. And because they're radial impellers, there'll be flatter curves, something like a 25% head rise compared with a 40% head rise for the Francis vane. Now, Ruhrpumpen has both designs available. Here is our German heritage design at about with a specific speed of about 1,000, and here on the right, our American heritage design, the Byron Jackson design, with a specific speed about 2,000. Here's a range chart for the semi-engineered or modularized range, the price list pump, you might say. Goes out to about 5,000 gallons a minute and about 4,000 feet head at 60 hertz. But we also have some much bigger pumps, the mixed flow pumps here, and these go right the way out to about 300,000, isn't it there, I think? 300,000 gallons a minute. Now, pumps are available either with above ground suction pipe or below ground suction pipe. So above is the mounting plate, so above ground or below ground. Depends how the user is running his pipework. Process pumps are almost always above ground. Below ground tends to be in water service. Now I've got a request for those of you specifying engineers. When you calculate your system NPSH, the available NPSH, you frequently tell us the NPSH available at the center line of the suction here, which means you're assuming a value for this distance. It's better that you give us the NPSH available at grade, and then we will calculate the necessary length to give you the required NPSH available at the first stage impeller. But with below ground suction, you're the guys who know where this pipe is, how far underground it is, so we need you to calculate the NPSH available at this point. And again, we will then calculate the additional length for to get sufficient NPSH available at the first stage impeller. Looking now at the barrel mounting flanges. Now, usually we have a square mounting flange on the barrel, and that would be set on prepared foundations. We can supply you with a sole plate, a square sole plate, which we ship in advance of the pump so that you can set it in the foundation when it is poured and level it. And then the square barrel mounting flange sits on that. Another option is that we can give you a steel channel frame, a base plate, and the barrel flange will sit on that. There's a fourth option becoming less popular now. In the 8th edition of API 610, it required a separate mounting flange. So instead of being this square flange on the top of the barrel, we had to put another one, something like 10 inches below. That's no longer required by API, but it's available as an option. It's still in some people's specs. Here we have 3 photos illustrating barrel installation. My thanks to Robert Bernstad of ITT Goulds for the photos. In the middle one, you can see the sole plate that was installed earlier on the prepared foundation and leveled. In the third photo, you see the square mounting flange of the barrel set on the sole plate, ready for the pump to be installed. And here comes the pump. These VS6 pumps come in API and non-API designs. The non-API is usually in water service, and it'll have threaded cast iron bowls. It will also have integral wear rings and taper lock bushes to fasten the impellers to the shaft. The API build pump will have flanged bowls. It will have replaceable wear rings on the bowl and impellers, and it will have ring and keyed impellers. Some manufacturers, Ruhrpumpen included, use a low NPSH first stage impeller to shorten the pump as much as possible. This specially designed first stage has been designed to have a wide operating range while maintaining good NPSH performance. Other manufacturers will use an inducer to do the same thing. How well this works depends on the design of the inducer. Historically, inducers had a U-shaped NPSH curve, which limited the operating region. You could probably only work to about 10 or 15% either side of the design point, so best efficiency point. But more recent designs have a much broader range. But the oil and gas industry is very suspicious of inducers, and many specs still forbid them. Here are the main features of an API build VS6 pump. So the API requires that it shall be ASME 8 stresses. It'll have an external seal chamber sized to take an API 682 seal, code certified welding, an 1/8" corrosion allowance, flanged bowls, separate impeller and case wearings, full range of API material codes, split ring and key impeller mounting, sometimes a separate mounting flange if you're doing an 8th edition pump, and the flanges shall be weld neck full penetration welds so that you can x-ray them when you want to. And here are some more features on the left and their benefits to the right. So 4-piece rigid adjustable coupling, maintains superior alignment, and the spacer allows removal of the cartridge seal. An API 682 seal, integral welded spider. I'll cover that a bit more later, but it ensures maximum shaft alignment and support. And this can be very important when you consider that this pump might be 30 feet long and it might be operating at 3600 RPM. So alignment is everything. And an integral welded spider, which, as I say, I'll cover later, is important in that. The API pump has carbon impregnated bearings throughout, Petrocoke. And this allows it to handle a wide variety of low lubricity fluids. So propane, butane, ethylene. Flanged and bolted bowls for all metallurgies, which is good for ease of maintenance with galling materials, especially as you might have stainless steel bowls in here. So galling is a possibility. Positive split ring and key couplings, split ring and key mounting of the impellers, which means that the thrust is transferred positively and it locates the impeller positively. Metal to metal rabbited fits with O-rings. Again, superior alignment, no leakage. Low MPSH first stage impeller for optimum efficiency and shorter pump length. And finally, a bottom case bearing, which we think is important. It gives shaft support at the critical suction area. If you are going to get any vibration through cavitation, it'll be down here. So having a well-supported shaft there will ease the problem. So what are the differences between the European, the radial, and the American Francis vane designs? Well, the European designs are usually with tie bolts. And often when lengthening the pump for MPSH reasons, they just lower the first stage impeller rather than the entire rotating element, as we do on the American designs. Seems to me there's no good reason to do it either way. Either way is equally good, in my opinion. Anyway, as European motors seldom accommodate thrust, a thrust bearing is built into the standard pump. And here is the non-API pump. We have cost savings achieved in this less arduous and less hazardous service. So we'll have, for example, slip-on flanges rather than weld neck flanges. We'll have integral wearings and we'll have collet-mounted impellers. All of these things keep the price down. Not shown here, we'll also probably have a flat plate at the bottom of the suction barrel with fillet welds rather than a full penetration elliptical end. So looking at collet-mounted impellers versus split ring and keys, the API pump will always have split ring and keyed impellers. Gives positive retention. This is important when pumping hot and cold liquids, and they're less susceptible to loosening when subject to a shock load. On the non-API, the water pump basically will have collet-mounted impellers, which give you ease of assembly and disassembly, gives good positioning of the impeller, a lower cost and easier for maintenance. It's a well-established design on hundreds of thousands of borehole pumps. Works really well, but on an API pump, you will have ring and keyed, locked and keyed impellers. But what about integral wearings versus renewable wearings? Well, you always have renewable wearings on an API pump, required by code. But on a non-API offering, we encourage integral wearings initially. When the first major overhaul occurs, which is probably after about 5 years, you machine and fit bowl wearings at that time. And then at the second major overhaul, probably at 10 years, you could machine and fit impeller wearings, or just replace the impeller with a new impeller to fit the wearings on the bowl. The nozzle head, well, being a fabrication, we can design and build it pretty much any way you want or specify. The API version has 300-pound flanges. It's designed for 40 bar. Could also have 600-pound or 900-pound flanges. They're all full penetration weld nozzles. On the commercial or industrial VLT, 150-pound flanges are standard, but you can get 300-pound. Both designs, the API and the non-API, still have rabbited or register fits for the motor to ensure good alignment. Here we see the elliptical end on the API version, which allows for a full penetration butt weld to the pipe. The non-API uses a flat plate as standard with a fillet weld. Now here we're looking at the top end of a column section. What you see here is the bearing spider, which is integrally welded and machined at the same time as the column flange. This ensures perfect alignment, which is very important when you consider that this pump, as I mentioned earlier, can be 30 feet long and running at 3,600 RPM. So no drop-in spiders with the Ruhrpumpen design. Some vendors do machine a recess here and put in a standard drop-in spider there. We like to weld it in place and this is on both the commercial VLT, the industrial VLT, and the API VLT. So welded in place and machined at the same time as the flange to ensure it's concentric. Mechanically seals. Well, the API version has seal chambers suitable for API 682 seals. VS6 and 7 pumps most commonly have a single seal with Plan 13 sealing system, which is flush from the seal chamber back to the suction. They'll often have tandem dual unpressurized seals, which would use Plan 13 and here Plan 52. And sometimes they have double seals, dual pressurized, which would use a Plan 53, 53A or B. Single seals can also often have a dry running gas seal as a backup seal with a Plan 75 or 76 to detect any leakage past the inboard seal. Now here you see the Plan 52 is mounted on a bracket on the discharge head. This isn't our preferred manufacturing way. This sort of cantilevered load off the side of a pump is not good for nozzle loading or vibration, but we can do it on larger pumps as we've seen here, but I wouldn't recommend it on a smaller pump. I mentioned earlier that the base design for the American design VS6 is with thrust taken in the motor. Most European and Asian motor suppliers don't have this construction as standard, so we have an optional construction with a thrust bearing in the pump. Here is a grease lubricated bearing used on the smaller sizes. You'll see it sits on top of the mechanical seal flange, like this. For the larger pumps, we have an oil lubricated bearing built into the motor stand, like this. And like this. Now, while we're on this slide, here is the barrel vent. This is a very important connection. The suction can of a VS6 pump should have a vent connection permanently connected back to the suction vessel, the original suction vessel, or to the flare system. It need not continuously pass fluid. You can fit a float type interceptor that will open to pass vapors but not liquids, for example. But the key point is you must never let vapors build up in the pump suction can. If you do, you've lost your NPSHA advantage. Your NPSH available will now be whatever the level of liquid in the suction can is, with no contribution from suction pressure. You'll probably cavitate. Finally for today, the VS7 volute type pump. Not nearly as common as the VS6. It has a double suction impeller, taking flow from below and from above. It leads to lower NPSH required, but it's a bigger diameter design than a diffuser design, and it's a heavier casting. So what you gain on the roundabout, you can lose on the swings. Not as extensive a range of hydraulics as the VS6s, but when it hits a sweet spot, it's a winner. Here is where they have an advantage. The single impeller develops the higher heads and capacities without the need for additional stages, frequently, which minimizes the number of wearing parts. As you see, here's the range chart, limited number of sizes, but quite extensive really. And the mid-range here is, 10,000 gallons a minute at 300 feet at 60 hertz speeds. Shown here is a two-stage pump on the left and a single-stage pump on the right. It's a double volute design, so we have 4 discharges, 1, 2, 3, and 1 at the back, which combine into a single outlet. And here, the second stage is a mixed flow design, a diffuser design. And here you have it as the first stage in a multi-stage pump with diffuser type series stages. Well, that pretty much concludes the fun for today. I hope you found it useful. I just get to advertise the short courses, which won't be until September. We're going to take a break during the vacation season of June, July, and August. Sucks being retired, you know, having these long vacations. I haven't decided for certain yet, but it's likely to be on performance testing and inspection of API 610 pumps. But I am also toying with the idea of pumping CO2, dense fluids, and compressible flow. That is a subject that will certainly stretch me academically. So we'll see what happens. Provisionally, we're looking at Thursday, the 11th of September, but we'll let you know nearer the time. We won't let you forget us. I'm going to leave this meeting open for a little while to allow you to post in the Q&A box, and I'll endeavour to answer those that only need a short answer here and now. Those that need a fuller answer will be answered in the coming days. Anything you do think of later, marketing@ruhrpumpen.com, or to me directly, smith@ruhrpumpen.com. Our marketing team are standing by to direct your questions or suggestions to the best person to answer them. And they'll be sending you the YouTube recording and a PDF of the presentation and the summarized Q&A from both of today's sessions. If you need a certificate of completion, again, short courses, marketing@ruhrpumpen.com. Here, right at the end, as usual, 8 slides that tell you what we do and who we are. I won't bore you with them. You've seen them before. They'll be in the hard copy of the presentation that you get. So now I'll stop the share and let's get on with the Q&A. Do we have any questions? Yes, we do. Paul Bertillon says, at which locations do you typically install the accelerometers to monitor vibration? On a VS6 pump, they would be on the discharge head, adjacent to the by the top. Start again. On a VS6 pump with a thrust in the motor, you'll put it on the top flange of the pump, which is also the bottom flange of the motor, because that's where the bearing is. You're looking for to get that vibration. Now, if there's a thrust bearing in the VS6 pump, then you'll put it on the flange closest to that bearing. Paul Bertillon again, for the VS6, are there acceptable methods to store the pump long-term in the horizontal position? Yeah, a lot of people prefer to mount them in a vertical position if you're storing a spare pump, but it does work perfectly well to store it horizontally. You'll put it in a well-protected box. It's worthwhile opening it every 6 months and rotating the shaft to stop it galling. Paul Bertillon says, which Ruhrpumpen facilities have the ability to acceptance test a VS6? Certainly Tulsa, certainly Monterrey in Mexico, certainly Witten in Germany. I'm not quite sure about our plants in Egypt and India, but I believe they do. One of my colleagues might ping me a message and let me know in a second whether or not that is the case. An anonymous attendee has said, for VS6 pumps, what else can be done to address potential alignment and vibration issues in the field, i.e. thrust bearing selection, bushing selection, vibration, instrumentation, etc.? Buy from Ruhrpumpen. No, buy from a reputable supplier. Flowserve, Gould's, Sulzer, as well as Ruhrpumpen, and did I catch everybody? Cool. And you shouldn't have a problem. They are problem solvers. They are very forgiving, and I wouldn't anticipate you ending up with problems. As regards to putting instrumentation on them, probably it's only worthwhile fitting accelerometers on the discharge head, I would say. One of my colleagues has come back and said that measuring at the top motor bearing and on the discharge head allows you to take readings and easily identify if a vibration issue is on the pump or is motor related. In other words, put an accelerometer. This is for a thrust bearing in the motor. So put an accelerometer at the top near the motor bearing and on the pump top flange, and then you'll see whether you've got a motor problem or a pump problem. I've also had a comment. Every single one of the Ruhrpumpen test facilities can test a vertical pump, apart from the one in the UK, which is a specialist facility for reciprocating pumps. So they don't have a pit. Manish Hingragia, I think it is. Excuse me if I've got it wrong. For VS6 pump design, if the pump is mounted in a module, does it help to have a separate mounting plate so the seal plan is easy to connect and the pump is easy to remove? I don't think it makes any difference to the ability to remove the seal or the seal plan. The seal plan will normally be mounted alongside the pump anyway, not hanging off the discharge head. That certainly makes it easier to be able to withdraw the pump if you haven't got a mechanical seal pot, a Plan 52, sitting on top of the hanging off the side of the pump. A mechanical seal is always withdrawable with the pump in place. You don't need to remove the pump at all to get the mechanical seal out. So it really doesn't matter. Chris Street says, thank you very much. Well, thank you, Chris. Thank you for attending today. Any more questions coming through? I think you let me off easily today. I have, of course, done this course before about 3 years ago, and we've had about 11,000 downloads of the materials for this for this session, which I have improved and upgraded for this one. I didn't just churn out the same one as I did 3 years ago. I did improve it. But here we go. Jeremy Koo says, is the coupling designed to only remove the mechanical seal? In the past, we're stuck with removing the housing and bushing. The complete mechanical seal cartridge will lift out through the through the spacer coupling. If you've got a separate thrust bearing, that will also come through the spacer. It's designed to come through the spacer. However, they can, on bigger pumps, they can be quite big and bulky, and sometimes it's easier to remove the motor and lift it out vertically than it is to try and get it out through the spacer. So it sort of depends on the size of the pump. Vanessa Marshall says, I've heard of resonance issues for large pumps with a mounting support. Any advice how to be proactive? Thank you for that. That's a good question. Yes. If it is a new design, you might say, one that hasn't been built recently, you can get a structural resonant frequency. You can hit a natural resonant frequency. So, for example, hanging the mechanical seal pot off the side of the pump, you might end up hitting a natural resonant frequency. I can remember a situation once on a pump that was running at, okay, it had been run at 3,600 RPM many times, this design of pump, with thrust bearing in the motor. Hundreds of times that pump had been supplied, and it had been supplied at 3,000 RPM, 50 hertz speed, with a thrust pot. And at 50 hertz speed, never a problem. Then one day we had a problem where there was a 3,600 RPM pump with a thrust pot. And that was the first time that combination had been done. And can you believe it? We hit a natural resonant frequency. So we did a resonant frequency analysis, and we worked out where we needed to either beef up or make more flexible the structure and take the natural resonant frequency 20% away from the running speed. It was an interesting problem, but yes, sometimes it will happen on a design that doesn't have a good installation list, you might say. It hasn't been done before, and it is a possible, but any reputable manufacturer will recognize that that's a problem, a potential problem, will do the analysis when necessary and either beef up or soften the structure. Thank you for that question, Vanessa. Olakuni Farayeni says, how do you address water ingress into the bearing housing of a VS6 pump and subsequently damaging the bearing? I'm trying to think how you get water ingress into the bearing housing. It's always, I mean, I take it you're thinking about a separate thrust bearing sitting on top of the mechanical seal. Well, the mechanical seal is stopping any any water that is being pumped. Again, if we're talking about a water pump, we're not talking about rainwater pump. If we're talking about fluid that is in the pump, it won't get past the mechanical seal. What it could do if the mechanical seal failed, but then yes, it is then going to probably ingress into into the bearing housing as well, and you'd have to dry out the bearings as well if you had a seal failure. Any more questions? Some nice, interesting ones today. Thank you. I do like I do thoroughly enjoy the Q&A session of these meetings. Okay. Olakuni Fadayeni says the water ingress is external from rainwater. Again, it shouldn't get into the pump bearing. You would have an impro seal or something like that at the top of the thrust bearing, so water would not get in there. You could also have a flinger there on the shaft, which would act a bit like an umbrella, if you like, to take the water away from the bearing housing. Okay, that does seem to be it, and it's 3 minutes to 6. And as you all know, 6 o'clock is beer o'clock here in London. So, oh no, I think it's another one's just popped up. Anonymous attendee says, "Does the line shaft bearing interact with the fluid?" Obviously, you need to make it of the right material for the fluid because it is wetted. Line shaft. If we're talking about a VS6 pump, the line shaft is wetted by the process fluid, and so it needs to be the right material. So if you need a duplex stainless steel pump because you're pumping seawater, then your line shaft will be stainless steel, duplex stainless as well. And in fact, the same would also be true of a VS4 pump. Although the shaft is only, you might say, dampened by the process fluid, you still need it to be of the suitable metallurgy, because whatever the level in the sump is will be the level in the column of the VS4 pump. Hope I made that clear. Sounds a bit rubbish to me. Julio Carranza says, "Thank you." Thank you as well. It's a good session today. My colleague has just come up with a good point. Less true on a VS6 pump, but if a VS1 pump, a borehole type pump or a long shaft pump, they'll frequently be supplied with an enclosing tube around the shaft, and with oil lubricated bearings or flushed bearings, so that it's not the process fluid, it's not the water that you're pumping that's coming in contact with the shaft. It is oil or clean flush. So that's for an enclosed line shaft on a VS1 pump. But we're talking VS6 pumps here, so they're normally open line shaft. Okay, I'm going to call it a day there. It's definitely 6 o'clock now. So thank you very much for attending today. I enjoyed preparing it and presenting it. I hope you enjoyed and found it useful. I'll see you in the autumn for the next sessions. Bye-bye.